Hi there. Welcome to Lecture 9 of Machine Learning from Data. We're going to continue our study of linear models with logistic regression, and we'll also introduce a general purpose algorithm called gradient descent, which is useful for minimizing functions, in particular in-sample error functions. Okay, quick recap from last time. Okay, we talked about the linear signal W transpose X and how it can be used to solve different kinds of problems. Classification, regression, logistic regression, which is the focus of today. Okay. Now, this lecture followed an entire theory on how we maintain this link from E in to E out. Okay? And basically, you need to learn with a hypothesis set that as small a VC dimension as you can get away with. Okay? And linear models are ideal for that. The linear perceptron VC dimension is just D plus 1. Okay? So now that you've got this, simple hypothesis set, how do you get the in-sample error small? And that's where the important takeaway from last time is, you have to construct good features. Features that are relevant for the task that we're trying to solve. Relevant for the problem that we're trying to solve. And we introduced the digits data, which we will be working with throughout the semester. Here are examples of 5s, here are examples of 1s, and we introduced features which are intensity and symmetry. Now we got those features without looking at the data, just thinking about the problem and what distinguishes a 1 from a 5. Okay, and this is just 2 features. So if you use a linear model with just 2 features, its VC dimension is just 3, and bam, you've got E in close to E out. And look, if you've chosen good features, you can get E in small. Okay. Now, on the practical side, we introduced the pocket algorithm, which is, now that you've gotten good features, you still need to go and find the hypothesis that gets the smallest in-sample error. Okay? And the PLA, when your data is not separable, goes on forever. The pocket algorithm can tolerate errors. It's simple, it's efficient. Okay? And then we talked about linear regression, where the task is to predict credit level, a real number. Okay? And the error that we use to measure how good are your predictions is the squared error. And we showed, or we derived the pseudo-inverse algorithm, this beautiful algorithm that, efficiently in one step, without using an iterative process like the pocket algorithm. So in one step, the pseudo-inverse linear regression algorithm finds you the weights that minimize the in-sample squared error. Okay? And so, one of the applications of that is to approach a classification problem as if it were a linear regression problem. Use the pseudo-inverse algorithm to get a set of weights, okay? And then use those weights as the initial weights in the pocket algorithm. Okay? So linear regression is in and of itself an important problem when you're trying to, for example, predict a credit level. Okay? And it can also be used as a startup phase for the pocket algorithm. Okay, today, logistic regression. And, let me give you this example where, someone's about to have a heart attack and we'd like to know what are the chances they have a heart attack over the next year. Okay, so here's a input. This person is 62 years old, is male, 120 milligrams, blood sugar, HDL, LDL, mass, height, You can think of this as the biological profile of your, your applicant in some sense of your input. Okay. And now, if we were doing classification, you should say yes or no. This person will have a heart attack in the next year. Okay. Now, in the logistic regression problem, don't tell me yes or no, will they have a heart attack? Tell me the likelihood of a heart attack. And if the likelihood is, let's say, 0.9, this person is in a serious situation. If the likelihood is 0.1, the person is not in a serious situation. So the output of the logistic regression is not a binary plus or minus 1, yes or no answer. It's a probability that's between 0 and 1. Okay, so how do we do this with the linear signal? We take the linear signal, which is W transpose X, and we pass it through a function, a sigmoid, what we can call a logistic function, okay, which takes the input W transpose X, takes the signal and transforms it smoothly into a real number from 0 to 1. Okay, so when W transpose X is very small, close to negative infinity, okay, you're going to output 0, and when W transpose X gets very large, you're going to output 1, and then it's going to smoothly interpolate. Okay, so let's move to the board to discuss logistic regression. We'll derive the error function, we'll derive the algorithm, and that's where we'll see that we need gradient descent. Okay, so logistic regression. And the task is to predict a probability. So here y is in 0, 1. Okay, and so the idea is you take the linear signal S equals W transpose X. So you take the linear signal, and apply a transform to it, goes to theta of W transpose X. And so our final H of X is equal to theta of W transpose X. And let's see what this function theta should look like. Okay, so on this axis, I will plot W transpose X, 0. Think of this as going to plus infinity, going to minus infinity. And, here I'm going to plot, so this is the signal. Okay, and I want it to go to +1, here. And I want it to go to 0 here. So this is 0, this is 1. Okay. Okay, and when the signal is very large, I'm at 1. And when the signal is very, very small, negative, I'm at 0. And I want to smoothly interpolate between those two. This is called a sigmoid. Okay, and you might think that, when the signal is 0, maybe it should be a half. That seems like a reasonable choice. So there are many choices of functions that we can pick that have this sigmoidal behavior. Okay? And so, this gives us a little bit of flexibility to choose a sigmoid that's mathematically convenient. There's no real reason to prefer one over another. And so the sigmoid that we're going to choose is a particularly convenient sigmoid. So theta of S has this mathematical form, e to the s divided by 1 plus e to the s. And you can easily verify that at the two limit, when s goes to infinity, you get e to the s over e to the s, which is 1. And when s goes to minus infinity, you get 0 over 1 plus 0, which is 0. Okay. Now, this turns out to have some nice mathematical properties. Let me just summarize them. Okay, so the first is that we can observe that this is equal to 1 over 1 plus e to the minus s. Okay, dividing top and bottom by e to the s. And so this means that 1 over theta of s is equal to 1 plus e to the minus s. So a particularly simple, convenient form for the reciprocal. Another useful property of this function is that theta of minus s is equal to e to the minus s over 1 plus e to the minus s. So I plugged in minus s here, which is equal to, if I multiply top and bottom by e to the s, is equal to 1 over 1 plus e to the s. And you see that if I add theta of s, so this guy, and theta of minus s, so this guy, I get 1. So this means that theta of minus s is exactly 1 minus theta of s. Okay. So, we get to choose the sigmoid to use because, we're building our hypothesis set, and all we really need is a reasonable sigmoid, and so we might as well choose a sigmoid that's convenient, and this is a particularly convenient choice for the sigmoid. And we'll see why as we, continue our analysis, why this is a particularly convenient sigmoid. Okay, so this just accomplishes the goal of getting the linear signal and outputting a number between 0 and 1. Okay. Now we need to do a couple of things. The first is we need to address the logistic regression problem. Okay, so how is it presented to us? And then the second is, just because I have a number between 0 and 1 doesn't mean it's a probability. So we need to address how we're going to get a probability. Okay. So, question 1. What's the setup of the logistic regression problem? So setup of logistic regression. And question 2, just any number between 0 and 1 is not going to be a probability. So how do we get a probability? How do we get a probability? Now, let's set up the regression, the logistic regression, and let's think back at that heart attack prediction. Okay, so, and let's think about how we would collect data. So how do we collect data? So we get a whole bunch of patients. Okay, and remember, a patient is represented by the weight, by the weight, the blood pressure, this, that. So the patient is represented, so you have a bunch of patients, just like applicants, they are input vectors, x1, x2, x3, up to xn. And we're collecting data. Okay. And now we're trying to learn a probability. So we're in this supervised learning context, and we would like you to tell us, for this patient, what's the probability they will have a heart attack? For this patient, tell us what's the probability they would have a heart attack. That would be the ideal data for logistic regression, because we're trying to learn to predict a probability. But I have news for you. We don't know how to measure probabilities. Okay. All we can do is take each of these patients, which are an input vector, and see what happened to them a year later. Okay. Did they or did they not have a heart attack? So, all we can observe, we observe y1, y2, y3 up to yn, and yi are, in the set -1 plus 1. That's interesting. Okay, we would like you to tell us data of the form, feature x and probability p of x, okay, for that feature. But we can't measure probabilities. We can only measure whether or not an event happened. Okay? So, where -1 is no heart attack, +1 is heart attack. Okay, and so what we observe here is that the data is exactly the same as if it were a classification problem. So the data is as though we are doing classification. It's as if we've collected a data set that would be the same data set that we would collect if the task was classification to predict ±1. But this is the challenge of logistic regression. We're not interested in predicting ±1 as we would have been with classification. If that's all we cared about, we just run the PLA or the pocket and we're done. We're not interested in predicting ±1. The challenge is we have to predict a probability from the same type of data, okay, that we would use if we were trying to predict a classification, heart attack or not. So it's the same type of data as classification, but we want to predict probability. And that's the challenge. So somehow, okay, from ±1, did the event happen or not, we have to tease out the probability. Okay, we have to somehow infer the probability and learn how to predict a probability, okay, even though all we can observe historically when we're collecting the data set for machine learning is whether or not the patient had a heart attack. That's the challenge of logistic regression. So it's important to understand this challenge, okay, is that, you don't get to observe probabilities, you get to observe whether or not events happen. Okay, so let's see how we're going to do that. Okay. Now, even though we observe, yi is ±1, actually, underlying this observation of yi is ±1, we're imagining there exists a true ground truth target function. So there exists a ground truth target function f. Okay, and in this case, so f of x, and in this case, we're in the probabilistic target function world, the non-deterministic target function world. So f of x is basically telling us what's the probability that you will observe +1. Okay, so the probability that you will observe +1 given x is f of x. So this is the case that the observable y is non-deterministic, but there is an underlying target function that we're trying to learn, which is this probability. Okay, and if there isn't such an underlying target function, if there's no pattern, then we're not in business anymore. Okay? And so, let's see, what would be the probability of observing -1 given x? Okay, so this would be 1 minus f of x. Okay, because f of x is the probability to observe +1, 1 minus f of x is the probability to observe -1. So even though the data is ±1, we're not trying to predict ±1, we are actually trying to learn f. This is the true probability. True probability. Okay, this is the true probability. Okay. And our goal, our hope, is that the h of x that we learn, so the hope / goal, is that h of x, which is theta of w transpose x, where theta is this sigmoid that we chose. Okay, so h of x is approximately equal to f of x. And then we have succeeded. We have constructed a function h of x, okay, by appropriately choosing the weights w, that approximates the true probability function f of x. Okay. Now, let's go back to, classification. Let's go back to regression. How did we go about picking the weights w that accomplished whatever the goal was? The way we went about picking the weights w that accomplished whatever our goal was to identify what's the in-sample error. In the case of classification, it was the fraction of mistakes you were making on the data. In the case of regression, it was the mean squared error, the average of squared errors, okay, where we were trying to predict a credit level. Okay, so and then what did we do? Then what we do is we say, oh, okay, so now that we've identified what makes a hypothesis look good, okay, i.e., minimize whatever that error is, then find the weights that minimize the error. Okay. Now, so our first task, if we're going to pick a final hypothesis G of this form, is we have to pick the weights for that final hypothesis. So we need to pick a final hypothesis G of x of this form, i.e. the weights need to be picked. Okay, and how do we pick those weights? Well, we need to identify what's the right in-sample error and then pick the weights that minimize the in-sample error. So need to identify E in of W and pick weights to minimize E in of W. Now, in the case of classification, E in of W was the fraction of mistakes you made on the data. Okay. In the case of regression, it was the average squared error. Okay, so what is the right E in here? So let me just walk you through that process. And in general, this is a good process to get a handle on. Okay. So, remember, h of x is supposed to approximate f of x. Okay. So that means that, the probability of +1 given x is supposed to be approximately h of x, and the probability of -1 given x is supposed to be approximately equal to 1 minus h of x. Okay, because h is supposed to approximate f of x. So, what this means is, now, if you observe a data point xn for which yn is +1, it seems more likely that, the probability of getting +1 is higher than the probability of getting -1. And so, this is going to be the likely outcome if h of xn is approximately equal to 1. And if you observe a data point, so remember, we only get to observe yn, which is plus or minus 1. If you observe a data point xn with yn is equal to -1, well, that's going to be the likely outcome if h of xn is approximately equal to 0. So, when yn is +1, h should be 1. When yn is -1, h should be 0. And we can summarize that by saying that h of xn should be approximately equal to 1/2 times 1 plus yn. Why? Because look, when yn is equal to +1, okay, then you have 1 plus 1 over 2, that's 1. Okay, and when yn equals -1, you get 1 plus -1, which is 0, so h would be 0. So h of x, or on the data, h of xn should approximate 1/2 1 plus yn. Okay. And so now we can easily construct an in-sample error. Look, E in of w, okay, or let's for the moment call it E in of h, but we know that, to specify h, you just have to pick a set of weights. W E in of h is equal to 1 over n, the sum from let's say from little n equals 1 to big N of h of xn minus 1/2 1 plus yn squared. Okay, so this is the remember, in regression, you try to get h of xn to be approximately equal to yn. Okay. Well, here we don't want h of xn to be approximately equal to yn. We're constructing the squared error so that h of xn is approximately equal to 1/2 1 plus yn. And that's a perfectly fine error to minimize. What it'll do is it'll ask h to be approximately 1 when you observe positive data points, and h to be approximately 0 when you observe negative data points. Okay, and this is, in some sense, you could think of that as the squared logistic regression error. The squared logistic regression error. Okay, and I just did that to show you the process by which we can derive an in-sample error to accomplish the task that we're trying to solve. But unfortunately, no, this is not good. Not good. Okay, and let me give you 2 reasons why it's not good. The first is just purely mathematical. It is an extremely inconvenient error. Because remember, why did we define this in-sample error? Was because that's the error that is going to grade hypotheses, grade different weight vectors. And okay, so now you've graded the different weight vectors. I need to go and pick the weight vector that got the best grade, that minimized this in-sample error. That's going to be very hard to do. Okay, and okay, so 1, it's not mathematically convenient. 2, where's the probability? All we did was we tried to make h of x and approximately 0 or 1 when, depending on the value of yn, but where's the interpretation of h of x as a probability? So it doesn't fundamentally use the fact that h of x is a probability. It does not use the fact that h of x is a probability. And so when we're done minimizing this, there's no sort of expectation that the h of x that we learn will correspond to actually a probability. It'll just be some function, okay, that equates to approximately 1 for all the data points that you saw that were +1 and approximately 0 for the data points that were -1. But where have we said anything about the probabilistic nature of h? Okay. So, I'll keep that on the board. And I'll tell you, what's the better error function? You might say, well, okay, so we derived this, it made sense, but then now you're telling us it's bad. So then what's the better error function? Okay, and I'm going to tell you. So